Okay, so this is actually referring us back to lesson 57, but because we just, I believe in lesson 81, learned the exponential growth and decay formula, I'm going to use that one, although you'll see that it really is the same one that you see in lesson 57. So the exponential growth function when you're using the natural log is n of t is equal to n sub 0 and then e to the kt. Now, we know that this is an exponential growth because it says to grow to 1,200 bacteria, and that's why we have a positive k instead of a negative k. Now, I am going to write the original equation down, which looks like this. Y is equal to a e to the kt. I think if you look in lesson 57, this is the equation that you'll find. But it's not hard to see that these equations really are the same thing. We're just using some different variables. And I actually prefer these variables because they're more intuitive, I believe. So let's start with the initial population. We know the initial population is 28, so n sub 0 has to be 28. We also know the final population after the given 45 minutes have passed. So this is n after t minutes, which is going to be 45. We have 572 here. We don't know what e is necessarily, except that it represents that value, that constant value, and then we have k, and then 45. All right. So here's the convenient thing about this formula, because we know what that e is a constant value. We can get this whole section all by itself. So I'm going to divide both sides by 28, divide both sides by 28, and I end up with approximately 20.43, but again, you're good at leaving these in your calculator, hopefully, so that you'll have fewer rounding errors. So we have e to the 45k. Now I get to take the natural log of both sides to get to this exponent. Whenever you have an exponent in the numerator, you have to take either the log or the natural log of both sides to access the ability to solve for that variable. So I'm going to take the natural log of 20.43, taking the natural log of e to the 45k, and as you well know, if this base is e and this is e, then the overall value of all of this is just whatever is in the exponent there. So we have 45k is equal to the natural log of 20.43. Natural log of 20.43. Divide both sides by 45, divide by 45, and now we should be able to enter all of that into your calculator. Natural log of 20.43 divided by 45. I came up with my constant as approximately 0.067. Okay, is equal to 0.067. Still haven't answered the question though. How long will it take the colony to grow to 1,200 bacteria? But we have almost all the components for entering it into the new formula. So we have n of t is equal to our original amount hasn't changed. We had 28 bacteria to begin with. We've got 20. We still have 28 as our original amount. We have e to the k. We now know the value of k is 0.067. Hopefully you have that stored somewhere in your calculator. And we've been asked, how long will it take? Clearly we're looking for the time here. And do we know the new final amount? Yes, we do. We know it's 1,200, and that's what goes right here. So if we rewrite this, we get 1,200 is equal to 28e to the 0.067t. Divide both sides by 28 again. Don't lose any of the algebra here that's going on. That should give us approximately 42.857 is equal to e to the 0.067t. Take the natural log of both sides to get access to this t in the exponent here. So now I have the natural log of 42. Whoops. Fix this here. Natural log of 42.857 is equal to. I'm just going to go straight to the fact that it's 0.067t. You understand what I did here? Let me just write it in here. Natural log, right? So that's how I was able to get from here to here. Now if you divide both sides by 0.067, divide both sides by 0.067, you should have a time of approximately 56 minutes, I believe. Hopefully you got that.